Good afternoon and thank you for joining me. My name is Roberto Ramos Chavez. I am a streaming engineer at Unified Streaming, a company located in Amsterdam, the Netherlands. And today I will talk about a scalable load generation framework for evaluation of video streaming workflows in the cloud. This work is a contribution to the Open Dataset and Software Track for MFC's 2020. And I will first I want to give an outline of what will be seen in this presentation. I will be answering some questions such as what, why, and how to build an open source framework for video load generation. I will first introduce some background and motivation for this work. Then I will provide some target requirements for this open source software and some constraints that the industry has shown. I will briefly explain the chosen open source software that was used to create this framework extension and other open source libraries used in this work. Finally, I will be answering the how-to of this framework by providing the parameter configuration and features of the software itself. I will present some use cases by using this tool, and I will present an evaluation of some experimental results that we carry out. Finally, I will end with the conclusions and future work. Background and motivation. First, I would like to give some numbers and trends regarding global internet traffic, but also the mixing of devices and connections increased by the following years. Today, global internet traffic indeed is dominated by video streaming with almost 71%, which is expected to reach 82 by 2022. A live internet, for one hand, will account for 17%, and 4K video content will account for 22%. The other 43% will be video traffic of gaming and other multimedia such as virtual and augmented reality. It's estimated also by 2023 that 60% of the installed flat panel TVs will be using UHD, which requires a higher bitrate, such as from 15 to 18 Mbps. The motivation of this work includes looking into some of the challenges that common over-the-top media services and IPTV broadcasters struggles with. For example, the deployment of video streaming at a scale in a cost-effective and reliable manner still remains a challenging task. Also, the increase of complexity for video streaming workflows that can increase the testing time before a production deployment. One characteristic or constraint from the OTT and broadcasters is the difficulty to assure prime time live events by any unexpected load generated, and challenging to test video workflows from different geolocations. So, what are the common questions raised when deploying an OTT media service? For example, how can a system under test can handle various loads, or how can emulate a realistic user load generation, for example, such as split run testing, or also known as A/B testing, which can be helpful to provide certain user behavior for the performance test, or other questions such as how many users can my deployment serve reliably without breaking. These and other similar questions are raised when creating OTT media services. Some current approaches to solve this kind of constraints can be divided into phases: the testing phase and the production phase. In the testing phase, we observe commercial load tools that have only one purpose, which can bring limited functionality and high cost. Additionally, common load testing tools do not scale or do not provide a flexibility for scripting user behavior. This is an example of A/B testing, as we mentioned before, to verify all use cases in a testing environment. On the other hand, the production phase, we can observe two current approaches. That one is the over-provisioning of cloud infrastructure that can at the end bring higher costs, and also the reduction of bitrate quality to certain users or streams. Open software proposal. Target requirements. We aim for a tool that can help identify three main aspects: segment availability, erroneous configuration, and or scalability issues. For the case of segment availability, we aim for a tool that can verify all available media segments for VOD and live streaming. In live streaming cases, we aim to identify request errors beyond the live edge or encoder discontinuities. For the part of erroneous configuration, we look into a tool that can identify CDN misconfiguration that can normally trigger overload at the media server, such as an origin server. And other aspects of erroneous configuration can happen, but here we give a couple of examples, such as system storage depletion that can lead to system failures, and also the slow backend storage access that can lead to delay and performance overhead. In the last part of the scalability issues, we aim for a tool that can help identify provisioning and breaking point detection, uh, also measuring memory leak or CPU increase in long-term testing. So Locust, why we have chosen Locust as our own main framework for video testing? So it's an open source framework that allows load testing of websites, and it is based on a coroutine-based Python library with an event-driven model. Additionally, it has a lightweight execution through microthreads, or also known like gremlins. It's easy to scale based on the number of computing nodes, and it can be run in the distributed mode through different locations. Additionally, Lucas provides a well-defined user behavior through Python scripting, so this helps to create different types of user scenarios for video streaming and any other A/B testing. Finally, the tool is well supported and documented. Locus can be run in a single machine or node, but also it can be run in a distributed mode with multiple computing nodes. In this slide, we can see Locus in distributed architecture that uses a master node, in this case, three slave nodes. Each of the three slave nodes communicate with the Locus master node by the Python instances. And on the other hand, each of the slave nodes will simulate the users provided through the configuration file. In the following figure, we present the architecture with the contribution extension. We show a master node with four slave nodes, and each of the slave nodes emulate an MPEG dash and HLS client by giving the master playlist for HLS and MPD for MPEG dash. So what are the features for this software contribution? First, as I mentioned, it emulates streaming protocols such as HLS and MPEG-. This is for the case of live and VOD cases. It emulates a buffer, which can be modified by its buffer size to understand startup playback or the behavior through a different buffer size. It can mix HLS and MPEG- to the emulated users with a radio assignment. It contains a bitrate adaptation of heuristic and the possibility to run from a different cloud server. For the parsing of the manifest files, we have used two open source libraries that I described in the bottom of this page. So what are the supported metrics by the software itself? The total number of accumulated requests and failed requests, the requests per second during time, the requests failed per second during time, statistics regarding the response time of each of the segment requests, and the number of failures for a particular request time. Parameter configuration. In this slide, I present two examples of how to configure the framework extension. The first example shows the configuration of a load test for an MPEG- live streaming, and the second example shows the load test configuration for a VOD HLS stream. More information on how to run the software or to install it can be found in the GitHub repository. In the right side, we see the table for configuration that shows the variable and values that need to be used in order to run the framework. Framework configuration. In order to run a full load test, you will need 5 steps. First step is to set up a publishing point of a server that can serve M3U8, MPD, and media segments by URA. The second step is to allocate computing nodes in any cloud provider such as Amazon Web Services and set up Locust software and the framework extension provided on the GitHub repository. The third step is to select the Python script that you will use to configure your load test scenario, as we showed in the previous command lines. And fourth step is to start the actual execution of the load test. And finally, wait until the test is finished to collect metrics in the master node. So how it looks like, we present 2 use cases. First, the gradual increase of users, and the second one that is users joining a video stream abruptly. In both graphs, the increase of users are represented by the green slope. But first, the left diagram of the first use case, we show the number of failures occurring after the number of users exceed the 500 number. This can give an estimate of the maximum number of users that this setup can handle with a specific load. On the other hand, the second use case, by users joining a VOD streaming abruptly, can show that the maximum response time before occurring any error is close to the 300 milliseconds for each segment request. Summary and future work. I would like to summarize what we've seen in this presentation. We have seen an open source load testing tool for live and VOD streaming cases. We presented 3 load testing use cases of a soak testing, a fixed number of users, and an incremental number of users. Multiple configuration capabilities based on the type of use case, and a tool that can be run through a command line and also through a Docker container to extend in different server architectures, such as a microservice architecture. So what's the future work? We're looking forward to see a faster HTTP client by using other libraries, such as fast HTTP or different Python libraries. This work can be extendable to other streaming protocols such as smooth streaming or HDS. We looking forward to detect with this tool breaking point detection for different setups and workflows and guarantee performance for all these setups. Thank you for your time. Thank you for assisting to this presentation. And in case you have any question, you have any remarks, please feel free to contact me through my email, and see you soon.